Hello everyone. Thank you very much for the invitation. So I'm going to talk about network with heterogeneous traffics under mixed delay constraints. And it's based on joint work with my PhD student Homa Nikpak and Shlomo Shammai. 5G is supposed to offer us three types of services. So we have the enhanced mobile broadband communication, which requires very high data rates. Then we have the ultra-reliable low latency communication, which in particular, of course, wants small delays and high reliability. And then you have the random access massive machine type communications. And in fact, the two first type of communications, they're supposed to take place on to share the same resources. So what we have to kind of design these two different traffics or data streams on the same spectrum. And this is basically what I'm going to talk about in this talk. And in fact, the standard proposition is to use some kind of time sharing and to use a smart scheduling algorithm on allocate or like on interleave the very low delay communication on the high rate communication. And so what we're going to see in this talk is actually by jointly coding the low delay and the standard delay communication, then actually we can get high benefits. At least under some architectures. In fact, we're going to look at scenarios or at networks with cooperation. So in 5G also, like our future versions of 5G, one of the suggestions is also to use like a cloud radio access network. That means that the mobiles, so they communicate to the base stations, but the base stations, they don't decode. Instead, they compress their signal, send them to the central unit, which then decodes all the messages. Or we can look at, in this talk, so we look at this one and also at the more classical cooperation scenario where base stations communicate over backhaul links, and mobiles, they might be able to communicate over Bluetooth or millimeter wave communications. So now that I talked, so we have cooperation, but then I said I want to have I have two different kinds of traffics, one that's very low delay. And of course, for low delay communications, we already have to shorten the packet length. So there's no, we can't have, we can't send low delay communication over multi-hops. So actually, the scenario we're going to look at is like we have two different kinds of traffics. One can take advantage of the multi-hop of the cooperation, and the other one cannot. So let me explain the setup in detail, at least the first setup that we consider. So we have a bunch of transmitters, and each transmitter has two messages. Like one with a superscript F, which is like the fast message, like the low delay constraint. And the other one is the message with the superscript S for slow, so the slow message. And the idea is the following. So we have, so we also have communication links between transmitters and between receivers, as we'll see. And the idea is the following. So we have these block lengths. And then, so the fast messages, as soon as they arrive, of course, they have to be sent within the next block length. They cannot wait. However, the slow messages, their transmission can be delayed. So basically, during this delay, they can profit. The transmitters can exchange some sort of cooperation information about these slow messages. Okay? So here, the first communication phase, thus is like a cooperation, interactive communication between neighboring transmitters, and this can only depend on the blue, on the slow messages. Okay? It's interactive in the sense that you send a couple of bits, and then you get a couple of bits back, and then the next couple of bits you send actually depend on what you send and the slow message. Okay? And these cooperation links, there are rate constraints, and we also limit the maximum number of rounds, DT. So once this cooperation is over, then actually the fast message. So we take the next fast messages that are about to be sent, and we encode them in one block length and send them over the network. The receiver, again, so the receiver gets a block length. It cannot wait with decoding. The fast messages need to be decoded immediately just based on the output signal. In contrast, the decoding of the slow messages can be delayed. So you can wait a couple of block lengths. In the meantime, you can do some talk to your neighbors, and then you decode your slow messages. So what we have these fast messages, and they cannot profit from the cooperation. So their encoding needs to be immediate, their decoding needs to be immediate. And then we have the communication of the slow messages. I mean, they cannot wait forever. We still have this Dmax constraint. So Dmax is a system parameter, is the maximum delay they can incur. But Dr and Dt, they're design parameters. So whether we want to have like more delay at the transmitter or at the receiver side. Okay, so this is the model we're going to consider. Maybe now let me just quick remarks about related works. So 2 years ago, we already had a work where we considered this problem basically with only slow messages. So when I say we consider this problem, it means like we limited the number of cooperation rounds. You know, like the cooperation we consider is like in Willem's seminal paper, but like in Willem's paper and many other related papers, the number of interaction rounds is unlimited. So here we limited it. And I think the work that is very much inspired, this one here, was a work by Hell and Steinberg. So what they have, they look at the broadcast channel with a cooperation link that might be present or not. And then, so you have to send messages to the receivers, and in case the cooperation link is present, you want to send an additional message to the receiver. So basically, you always send a message, and if the cooperation link is present, you send another message. Our setup is a bit different, so we have always two messages. One can profit from the cooperation, the other one cannot. And then I also want to mention this work by Cohen, Steiner, and Chamay. So it also does a joint design of the fast and slow messages. It's on a point-to-point link on a fading channel, and basically it codes the fast message just over one block and the slow message over a multiple coherence blocks. So block means a coherence time. Good. So what are we interested in? So on the networks I told you before, each transmitter, I hope you remember, had two messages, a fast one and a slow one. And so we have two rates. So here we have a rate RS, which is the average rate of all slow messages. We have the rate RF, which is the average rate of all fast messages. And so we have a capacity region. We're interested in what is the set of pairs, of rate pairs that we can achieve. So obviously, we can have the maximum slow rate. And in fact, many, as I said, sometimes it's already known in the networks you're going to consider. Or we can have this point here, which just is the maximum fast rate that you can have over the network without cooperation. And then a trivial inner bound is the time-sharing line between these 2 points, okay? So this is the standard approach. What is the problem is actually you see, because typically this RF is smaller than the RS, then actually this time share, so some capacity on this line decreases the more you move to you more increase RF, okay? So for example, if RF is half of RS, any additional bit of fast message you want to send, you have to pay 2 bits of slow message. And so the sum rate decreases also by 1 bit if you increase the fast rate by 1 bit. So we hope we can improve over this time-sharing line. So that's the goal. The best we can hope for is this dotted or dashed region here. So this is dashed region. This is a trivial outer bound. So this we have the constant sum rate, because the maximum sum rate is obviously obtained at the 0 RF point, only RS, because there are more constraints on the fast than on the slow messages. So this is this constant sum rate, the slope -1. And then another trivial bound is this, like the RF cannot be increased by sending also slow messages. So we have this vertical line. And so the point we really would like to communicate at is actually this corner point. So in this corner point, we can have the maximum fast rate without a decrease in the sum rate. And actually, we'll see that in some cases, we can achieve that point. OK, so this is the first network. We'll look at more complicated networks afterwards. Is this Wiener Soft-Handoff network. So here, so the transmission at any receiver k is only interfered by its left neighbor k minus 1. And then we have some additive Gaussian noise. Of course, inputs are power limited. And so let's first assume or look at the case where we only have receiver conferencing, so no transmitter conferencing, maybe because mobiles cannot communicate. And then we have an inner bound and an outer bound here on the left, on the right side of your slide. And unfortunately, they don't quite match, but we can get some insights, especially if you look at the inner bound. So if you see for small RF, the slope is actually -1. You see it because this is 0.36, and this direction is also 0.36. And in contrast, then actually, so the slope gets more and more negative the more you increase RF. And here, for large RF, you get a slope of -2. So in this regime, actually, you have to pay, if you want to increase the RF by delta, you have to decrease the RS by 2 delta. So you have the penalty in sum rate by a delta, okay? And so this is, so it's an intuition. Actually, so the problem here is a bit that our inner and outer bounds, they don't match. So intuition is always a bit delicate. So when I actually go to the high SNR, then the whole thing crystallizes. And moreover, we get matching inner and outer bounds, so we can make a precise statements. Okay, high SNR asymptotics means that the rate, the cooperation rate, actually grows logarithmically with the power p. And mu is this pre-log factor. And then we have the DOFs. We're interested in these pre-log factors of the rate. And so this is the region. So when mu is large, so mu is the rate, the pre-log of the cooperation link, then we get this blue region. And you see, and when the mu is a bit smaller, then we get the black region. They are similar in the sense at the beginning for small SF, so this is the pre-log of the fast message, we have a slope of -1. So we have a constant summary capacity, or a constant sum DOF. But then at some point, actually, you start to degenerate. So this is the maximum point of max sum DOF you can have. You have a slope of -2, okay? So in the first regime, the sum DOF stays constant. Afterwards, you have to pay. For every increase in SF, you pay the same decrease in the sum DOF. Okay, so in terms of, so the scheme, what is it? So these points, we already had it from our previous work. And then, so the important things were, like, the interesting thing was to get this point, but actually turned out to be kind of easy. What we did, we looked at the scheme that only sends slow messages, and then we realized that some messages actually were never involved in the cooperation. So you could be decoded without cooperation, and therefore you could replace the slow messages by the fast messages. So it was kind of for free. So this gave us these corner points. And then the converse results, so this is also like the constant here, this slope -1 is also easy. It's just like you cannot be better once you have the upper bound on the slow rate. So the main contribution is this slope -2, okay? So here, you see, it's actually, you can prove it in a few steps. So basically, what you have, I mean, let's not go through the steps, but what you can notice is, like, so the transmission from transmitter K, so this is the transmission from transmitter K, and then we look at its impact on the transmission of the fast message of transmitter K+1, right? So it interferes. And actually, so this interference just means, like, because the fast message doesn't have cooperation, so whatever you send on its right neighbor is going to cost almost the same DOF on this K+1. So it's like a standard interference converse argument. Good. So this was for receiver cooperation. Now we could look at the same question for transmitter cooperation only in this Wigger Soft-Handoff network, and we get exactly the same plot. So there's a duality between transmitter and receiver cooperation. Actually, we have observed that in previous works, and many other people have too, so this is no surprise. What we also observed in previous works is when we only looked at the slow messages, is actually that these points here, they only depend on the total delay Dmax. So you could also look at cases where you have transmitter and receiver cooperation. It only mattered, only the total delay mattered, but it didn't matter how it was distributed between transmitter and receiver side. So of course, since that's what we're used to, we thought the same applies here. We tried very hard to find the converse. We couldn't. Because actually, so if you look at this, so this is just one of the two plots. So if transmitter and receiver cooperation, it looks like we can achieve this corner point here, which is the optimal thing, the maximum we were hoping for, okay? And so let's look at the case with transmitter and receiver cooperation on the same network. So we can have this whole region here. And this, I think, is, so I liked it because it means that you can have the maximum fast DOF without any expense on the sum DOF. Okay? So this holds when you have enough cooperation prelock. If you have slightly less cooperation prelock, then actually you have to pay a little bit, and you get something that looks like the black curve. Okay? So now let's look at some schemes still. So what we are interested in is this, what I want to explain is how to get to this, that doesn't work, to the, yeah, this one, to this point here, okay? So this point here means I want to send at maximum fast DOF. And then additionally, I can basically add also some slow messages. And they're not going to disturb the fast messages, because otherwise they would destroy their DOF. And moreover, on the slow DOF, on the slow messages, I can do as good as if I didn't have these fast messages. And so this is the scheme. Okay, so I want to get SF equal to half. The only way to get this is actually to simply switch, so if I only have these fast messages, the way to get is you switch off every second transmitter, because you only have this simple interference pattern. This actually decomposes the network. And now I want to add these slow messages. So I put them on the even transmitters, right? On the even transmitters, but now I'm causing interference. So this communication is going to interfere here, right? And so actually this arrow should be blue and red. But so what do I do? So because I now have transmitter conferencing, I just describe it to the next, and this will just subtract it from its own signal. So just do pre-canceling, okay? And then this makes it this here. You canceled the interference of the slow on the fast. So you just do it here. You describe the signal, and then you cancel it, and you get an interference-free signal. So now the fast are still interference-free, and I get the half DOF on the fast. So what do I do on the slow? So the slow here, if you see, the red is interfering here. So this also gets influence from the red. I don't want that, right? So I just, to the receiver side, I can, because after decoding the fast, I can actually send them to my neighbor, right? They're decoded, and I can send them to my neighbor. This doesn't violate the delay constraint, and so you can subtract it. And so now I just have a bunch of somehow interference-free signals. So actually, I'm a bit cheating, because so the red are really interference-free. Right? But the blue are not, I mean, blue interferes with blue. Because look at this, so this is all good, but then this I sent it here, this subtracted the signal, and so basically over this crosslink is going to interfere here. And this one here, I send it here, it's going to be subtracted, it's going to interfere here. So really for the blue messages, what I have is something like this. But this is exactly what I started, just like only every second hop on transmitter-receiver pair, and I only have slow messages. But this we've solved in a previous work, and I know how to do that. So with some rounds of successive interference cancellation, dirty paper coding, and so on. And this is how I can get the maximum sum DOF. Okay, so let's go now to this cellular model. So here we have a hexagonal model. So each hexagon here is a cell. And then each cell has one base station, but the cell is divided into 3 sectors. And each sector has one mobile. We assume that the base stations, they have directed antennas. So this means that the mobiles within a cell, the mobiles from different sectors within a cell, they don't interfere. Okay? So this means here, if you look, this does not communication does not interfere with this one, and does not interfere with this one, and so on. And then, as before, we again assume we have cooperation between transmitters or between receivers. And some Gaussian noise and static channels, everything is known. And so we play the same game. We again have each trend, a mobile has a fast and a slow message, and the question is what is the DOF? And we get the following inner and outer bounds. So the solid line are inner bounds and the dashed are outer bounds. And so for high cooperation rates, thank you, for high cooperation rates, we get something that looks like this. So what we have is actually, so this is the point, so this is what you get with interference alignment, right? But interference alignment, so people tell me you cannot implement it in practice because it needs infinite symbol extension. So and if you just look at interference avoidance, this is really the maximum point you can have. And for this maximum point, actually, we get it at maximum sum rate. So we have similar conclusion before. And I want to show you how we get that, okay? It's a similar idea as before. So we have this hexagonal model, and what we proposed in a previous work, so actually now I first explain how to only send slow messages. So we silence some of the users, okay? And this will actually give me, so these joint clusters, which we call the wind spinner clusters. And then within a cluster, each base station, so mobile users just send Gaussian signals. Each base station quantizes its output and sends it to the center base station, jointly decodes, and then tells everyone what its decoded message was. Okay, and this gets you this point. And so what we do now that we have fast messages, so first of all, as before, we distribute the fast messages in the same way that as they were, so to avoid that they interfere. And actually, we can put a fast message on every third sector. And so they don't interfere. Just notice these two don't interfere because they're in the same cell. And then the rest is slow messages. And so the scheme goes as before. So each slow mobile sends its message or its signal to its fast neighbor. The fast neighbors can pre-cancel it. So so in the fast sectors, we get interference-free signals. And then these decoded fast messages are sent to the neighboring slow sectors, so they can also cancel it off, and then we can just do what we did before. So we send everything, all the slow messages are decoded at the central point. And we get this point here. Okay, so I think I have maybe 3 minutes left? Yeah, okay. Yes, so this brings me to, so of course, what I said before, you can play the same game with other networks. Another setup that you consider was this cloud radio access networks, okay? So here, the delay basically comes from this hop, additional hop from the base stations to the cloud radio unit. And the requirement now is that the fast messages are decoded by the base stations, whereas the slow messages can be decoded at this cloud processor. We can jointly decode them and therefore cancel some of the interference. And so a similar model or similar actually decoding, I think actually the same decoding constraint was also considered in this paper here. So here we also looked at the influence of fading. So here the channel coefficients, GK and FK, they're actually fading coefficients. And so yes, so there are two more things I want to mention here. One is, so we are back to the setup where we only have cooperation at the receiver side. Here the transmitter cannot cooperate. So just remember already before, we didn't have a huge gain here. And the other thing is, like, sometimes actually here, the fast message is not inherently more constrained than the slow message. Because if these rates are small, then actually the fast messages are in a better shape than the slow, because you cannot send anything. Okay, so this is the DOF region for this setup. And you see it's the time sharing region. You cannot do better than time sharing. Okay? I mean, good thing is that after the bad news, we have the good news. But that's how it should be, right? And so if we go back, so if you step back now that we're finally back to the finite SNR case, so in the finite SNR case, actually, we have again our gain. So here you see at least, unfortunately, our outer and inner bounds are really far. So I think we need to improve a bit more on our inner bounds. but still, the thing we can get is like, for what we have now, so the inner bound here, you have the slope -1 at the beginning. So if the fast rate is not too high, you can actually, you don't have a decrease in the sum rate. Then afterwards, once you actually come to this regime where the sum rate decreases, the decrease is actually much more rapid than before. So here we have the slope -4, it's just because we have more interference. Yes. Oh, yes, good. So 0, this brings me to the conclusion. Maybe half, okay, good. So basically I showed that by jointly designing this mixed delays, mixed delay traffic, so the encoding of these mixed delay traffics, we could get some benefits. Of course, for future works, we could make finer measurements of the delay, because now it was just in terms of hops. This will bring us maybe a finer block length regime, or we could also think about the more stochastic arrival processes. And with this I conclude. So if you're interested in the publications, it's here.